Okay, beginning from where we left in the previous session. So, just a brief recap of the previous three sessions. So, first I defined what a signal was, right, and then I classified them into two broad names, right. So, one was analog signals, broad classes. So, one was analog signals, second was digital signals. So, I told you the differences, and next we moved on to define a system. So mathematically I described what a system is. It's basically it's a system which takes one input, okay, and transforms it into another form which we called as an output. So basically mathematically if we describe it, y of t was transformation acting on the input signal x of t, right. And then we looked at two important properties. So one was the linearity property, where we defined the linear systems as the systems that satisfy the input output relation, satisfies two principles. One is the principle of homogeneity, and the second one was principle of superposition. Both are necessary and sufficient conditions for a system to be classified as a linear system. Okay, moving on. So we looked at another property of systems which was called the time invariance property. Okay, so I defined what time invariance means. So if we the definition goes as follows. So if we shift the input by some amount, the output should also be shifted by the same amount. Okay, so in broad sense, so if we looked at the shape of the output waveforms in both the cases, when we feed the input and the shifted version of an input, right, the shape of the waveform should remain the same, right. It should just be shifted along the time axis to the right or to the left by the same amount which you shift the input. Okay, so that was the definition of time invariance. So we'll just look at two examples, right. So on how to check whether a given system is time invariant or not. Okay, so what will be given usually is, so you will be given a relation between the input and an output. Okay, sorry. Okay, so and you have to test, since you know how to classify a system as time invariant or time variant, right. So test that condition. If it satisfies the condition of time invariance, then the system will be a time invariant system. Okay, so first example. So this is from a book that I had told you in the first session. So one book is enough. So it covers all the information that I am giving you in these sessions. Okay, so the textbook was Signals and Systems by Alan V. Oppenheim, Alan S. Wilsky, and Hamid Nawab. Okay, so the three authors, right. So it's a standard textbook followed in almost all the universities. Okay, so first, so I have a system, right. Let's call the system S, and it takes an input x of t and transforms it, which we call it as an output y of t. And what will be given is the relation between the input and an output. So in this case, the relation between output and input is, so y of t is equal to sine of x of t. Okay, so this is what the system does, right. Okay, so how to so your problem is to find if the above system is time invariant or time variant. Okay, so this is your job or the problem at hand. Okay, so to do that, so what I'll do is I'll shift the input first and feed it to the system. Okay, so I'll shift the input where t0 is some constant value, right. I can shift it by any amount, so I'll shift it by t0 units, and I'll call it as, since t0 is a constant, so this will be a function of time. I'll just call it using some other variable. I'll call it as x1 of t. Okay, and I feed it to this system S. Okay, now So when I feed the input x1 of t to the system S, I'll call the output as y1 of t, okay, which is nothing but sine of whatever you are feeding, right? That's the relation between the input and an output for the given system S. Okay, now I will substitute for x1 of t. So my y1 of t is nothing but sine of x of t minus t naught. Okay, so this is my output due to shifted input. So shifted by how much units? So t naught units, shifted input. Okay, now what I'll do is, I know that when I feed x of t, my output will be y of t. Now I will shift y of t. Okay, so if I shift y of t, what will happen? My output will be, so it basically means, so if I am taking the output at t equal to 3, right? So I'll substitute sine of x equal to sine of x of 3, right? At t equal to 5, if I want to find out the output of a system, I'll find out sine of x of 5. Okay, similarly, if I want to find the output at t minus t naught, so this will be sine of x of t minus t naught. Okay, right? So now, if I shift the output by same amount, it is same as the output I get when I shift the input by the same amount. Okay, so now, since both the outputs are same, right? So the system is time invariant. Okay, right? So the behavior of the system doesn't change when you shift the input signal. Okay, now let's take another example. So this will be a discrete time case. Okay, so as I told you in the second session, so a discrete time system is a system that takes discrete sequence as an input and gives you the discrete sequence as an output. Okay, so another example. So these examples are available in on page number 51 of the textbook that I mentioned. Okay, so the edition is second edition, right? So again, so I have a discrete time system which I call S. Okay, obviously the system in the previous example is different from the system in this example, right? So I have x of n and y of n. Okay, and the relation given is my y of n is equal to n times x of n. Okay, now the problem is the same, to find whether the system is the time invariant system or the time variant system. Okay, let's find out. Okay, now again I'll define. So if I feed x1 of n, my output, I will call it as y1 of n, whatever x1 of n may be, right? So no matter what x1 of n is, so if I feed x1 of n, the corresponding notation for the output will be y1 of n. If I feed x2 of n, the corresponding notation for the output will be y2 of n, so on and so forth. Okay, right? Now again I will use the same procedure. What I will do is, I'll shift the input first. Okay, by t naught units and find the output. Okay, so what I'm going to do is, I shift the input. Okay, right? So I'll call it as some x1 of n. Okay, because n naught, oh sorry, I'll write it as n naught. So it's just an habit since I was referring to the continuous time examples. So I wrote it as t naught. So the usual notation for discrete time, discrete time sequences is n, Okay, since it's an index, so n can take only integer values, whereas t naught can take any value, any real number as a value. Okay, now I'll shift x by n naught units. Okay, I'll call the input as x1 of n, since it's only function of n, because n is the only variable, n naught is a constant. Okay, so I'll call the output as y1 of n. Now notice, so if you are finding the output at index n, right, so the index is getting multiplied to the sequence, to the input sequence. In this case the input sequence is x1 of n, right, and I'm trying to find the output at index n. Okay, now so the output will be n times x1 of n. Okay, because my y1 of n, the output y1 of n is corresponding to the input x1 of n. Okay, now I will substitute for x1 of n, which is nothing but n times x of n minus n naught. Okay, fine. Now right, I shifted the input in the first step, I shifted the input by n naught units and found out the output of the system. Right, now I'll shift the output y of n by n naught units and check whether both the outputs are the same or not. If both the outputs are same, then the system will be time invariant. If both the outputs are different, then the system will be time variant. Okay, now I'll take the output y of n and I shift it by n naught units. Okay, now mind you, here, right, so I was finding the output, I just used a different notation, you can call it y1, p1, q1, it doesn't matter. Okay, what matters is the index n. Okay, now, right, so I shifted the output by n naught units. Okay, so now the instant at which I am measuring the output is not n, it is n minus n naught. Okay, which means my output will be n minus n naught into x of n minus n naught. Okay, fine. Now I'll compare this as well as this. Okay, so mind you, here in the previous case I had shifted the input. Okay, but the shift in the input did not reflect in the output. Okay, my output was still y1 of n. Okay, now I have shifted the output, okay, by n naught units. Okay, and this output I am going to compare here, right. So if both the outputs are same, right, then the system has to be time invariant, but in this case the outputs are not same. I have an extra term minus n naught into x of n minus n naught. Okay, hence the system is time variant. Okay, right, so that is how you find whether a system is time invariant or time variant. Okay, so if the output, if you shift the input by same amount, the output also has to shift by the same amount, whereas that didn't happen in this case. Okay, so when I shifted the output, I got a different output. When I shifted the input and found out the output, I got a different output. Hence the system has to be time variant because it is behaving in a different way, right. Okay, so in the first case, so if I look at the system at time instant n, right, it is behaving differently. If I look at the output at a system n minus n naught, right, at a time instant or index n minus n naught, it is behaving differently. Okay, so which means the system is time variant. Okay, so that didn't happen in the first example. So you think about it, right, solve one or two examples. If you have any queries regarding this, right, so solve more problems, right, so and try to interpret the results, so you'll get to know this better, right, the concept of time invariance. Okay, now we are in the next session, what we are going to do is we are going to use these two properties. Okay, so to find the input output relation of a class of systems called as the linear time invariant systems, which are shortly called LTI systems. Okay, fine. So we'll stop here.